Hi, Virtual Academy students. It's Ms. Macaulay, and I'm going to be going over the chemistry limiting reactant stoichiometry problem. I'm on the version of the doc that I retyped to show the BCA table, and it's super similar to the last problem you did on stoichiometry. It's just that this time we don't tell you what you run out of. So that's kind of the whole point. We have this reaction right here, this equation. This is an acid-base neutralization, which we'll get to in the next couple units. But we have sulfuric acid combining with sodium hydroxide. So here's the acid, here's the base, and they're going to produce water and sodium sulfate. So we're going to show all of our work in this problem. And the very first step is identifying the limiting reactant when 9.65 grams of the H2SO4, sulfuric acid, reacts with 6.10 grams of the base sodium hydroxide, NaOH. So here's your first hint. We don't know which of these is going to run out first. We might have left over this, we might have left over that, maybe they'll both work out, but we have to figure that out. And the way we do that is honestly just guess and check. So here's a hint. First, we have to convert both quantities from grams to moles and then plug it into the BCA table. So we're going to do a conversion, a little dimensional analysis here, taking our grams of sulfuric acid, and we want to cancel grams and get to moles. So for my conversion factor here, I have grams on the bottom to cancel and moles on top. So I need to get the molar mass of H2SO4. So I'm going to go to my periodic table. Right here we've got H2SO4. So we have H2SO4. So there's 2 hydrogen. Hydrogen's mass is 1.01. There's 1 sulfur. Sulfur's mass is 32.07. And we have 4 oxygen. Oxygen's mass is 16. So we add all those up and we find that sulfuric acid, its molar mass is 98.09 grams per mole. So let's do our color coding here. 98.09. Okay. 98.09 grams per mole. And so then we're just going to put that in our calculator. So we have 9.65. Now before you put this in, let's make a guesstimate. I'm taking 9 and dividing by 90. What would 9 divided by 9 be? 1. So what's 9 divided by 90? 0.1. So before I plug this in, I'm thinking my answer is less than 0. It's something like 0.1-ish. Not exactly, but somewhere around that. So 9.65 divided by 98.09. And I get 0.098. Is that pretty close to 0.1? Yeah, that's pretty darn close. That's a really important skill to have, is to be able to guesstimate what your answer should be around so you can figure out if you made a silly little calculator mistake. So 0.0983. 0.0983. Now, they gave me 3 sig figs in the problem. I want to have at least 3 sig figs, if not more. Ooh, now you see how it goes 790? I can either round that to 8 right now, but it's not good to round yet. We want to keep as much info as possible. So let's do 983. We'll do 79 for right now. 79 moles. Okay, that's going to be a value we can plug into the BCA table. Now we've got to do the exact same thing for the sodium hydroxide. So we have 6.10 grams of sodium hydroxide, and I want to convert to moles. So here's my conversion factor. I'm going to cancel grams and go to moles, and I need that molar mass from the periodic table. So we have sodium hydroxide, NaOH. And so sodium, molar mass is 22.99. There's 1 of them. There's 1 oxygen, its mass is 16. And there's 1 hydrogen, its mass is 1.01. Add them all up, and you get 40.0 grams per mole. Okay, so 40.00 grams per mole. So now, same thing with our calculator. We need to take 6.1 divided by 40. So kind of do a guesstimate first. Is this going to be more or less than 1? It's going to be less than 1, right? 6 divided by 40, going to definitely be less than 1. So 6.10 divided by 40.00 equals 0.1525. Well, that's nice. It has at least 4 sig figs there. 0.1525 moles. Oops, that was a crazy looking 0. 0.1525 moles. And remember, that's moles of our sodium hydroxide. We should be careful with our labels. Over here, I should have also labeled this as our H2SO4. Okay. So far, what we've done is we've converted the grams, which you would measure in the lab, to moles, which we can do our calculations with. Now, just kind of take a quick little look here. It looks like we've got a lot more, not quite double, of the sodium hydroxide. Okay, so maybe that'll be what's left over. But then look back to the equation. This is balanced for you. So if there's nothing there, remember it's a 1. So for every 1 sulfuric acid, I need 2 sodium hydroxides. Okay, so that's interesting. So let's go down to our BCA table and plug this info in. So 0.098379. So before the reaction starts, I have 0.098379. And remember, only moles go into the BCA table. I'm going to leave off my units here so it doesn't get too crowded. And how much sodium hydroxide do I have? I have 0.1525 moles. So what we have to do right now is pick, and we're just going to pick one and say, this is going to be the limiting reactant. Okay, I'm going to do a little trick to kind of show you how you can guess and check it. So let's say we are going to say we run out exactly of the sulfuric acid. We used it all up its limiting. So 0.098379. If that's the case, I need exactly double that amount of moles of the sodium hydroxide. That means I would need 0.19 or 0.2 moles of the sodium hydroxide. Do I have that much? No, I don't. So what that means is I can't use all this up. I'm going to run out of the sodium hydroxide. This can't be my limiting reactant. That was just a little guess and check I did. I'm going to go through and I'm actually going to pick the wrong limiting reactant to show you what happens if you do that and how you can fix it. Okay, so let's just say, oh, this is my limiting reactant. I'm going to label it LR. So before the reaction starts, I have 0.098379 moles of sulfuric acid. I have this many moles of sodium hydroxide. And before the reaction starts, I have no water and I have none of this salt over here. What happens during the change? I'm going to use up all of that sulfuric acid. So before the reaction, I had this much. During the change, I use it all. After there's 0, it's limiting. Okay, now how do I use this number? So that's always going to be my coefficient. So I'm going to be subtracting 0.098379 times the mole ratio. So times 2/1. Okay, and so we got to kind of figure out what this number is right here. So what is this number? We just had it in our calculator, I think. Oh, I closed my calculator. Okay, here's the calculator. So 0.098379 times 2. Now we don't really need to divide by 1. So how much sodium hydroxide am I using up? 0.196758. So 0.196758. So that's how much I'm using up. So how much is going to be left over? 0.1525 minus 0.19675. Oops. Now, minus 0.196758. How much is left over? Negative 0.04. Can I have negative 0.04 moles left over after a reaction? No way. So this means you chose poorly. That's okay. If you ever can't tell, you just pick one thing to be a limiting reactant. You go through the first half of the problem. And if you get a negative, it means you chose the wrong one. So what do we know now after that guess and check? We know what the limiting reactant is. So let's get rid of this. My limiting reactant is not the sulfuric acid. It is the sodium hydroxide. So I like to always kind of outline my limiting reactant because everything is based off of this, okay? It's like if you're making brownies and you don't have, let's say you have infinite water, infinite oil, infinite boxes of brownie mix, but you only have 2 eggs, the eggs are going to limit how many brownies you can make. Here, the sodium hydroxide is going to limit how much of this reaction can take place. So we've kind of seen now that sodium is limiting, sodium hydroxide. So before the reaction started, I had this many moles. During the change, I am using up exactly all of that. It will run out. It is the limiting reactant. So how much is left over when I'm done? 0 moles of my sodium hydroxide. Okay, nothing else changed here. This is still how much we're starting with. We still don't have any products before we start. During the reaction, I'm going to be creating water. I'm going to be creating sodium sulfate. And at the end, I'm going to have some positive number left over. Okay? And during the change, I'm going to be using up some of the sulfuric acid. So let's go back up and remind ourselves what it's asking. Okay, identify the limiting reactant. The limiting reactant is sodium hydroxide. Okay, we can label it up here, but we also have shown that in our work right here by labeling it. Number 2, what is the theoretical yield of sodium sulfate in grams? And how much excess reactant will be left over? So we need to fill out the whole table here to be able to answer those next questions. Okay, so this is my limiting reactant. Everything is based off the moles of this. Okay, so let's set that up. So how much sulfuric acid will I be using up during the reaction? I'm going to be using up 0.1525 moles times the ratio of the unknown sulfuric acid to the known sodium hydroxide. Where do I get that ratio from? I get it from my balanced chemical equation right here. So the 1 sulfuric acid, the 2 sodium hydroxide, see how that red cancels out? That's how much I'm using up, okay? Let's actually put this into a number so I don't make any silly mistakes with my calculator here. So we have 0.1525 divide by 2. I'm using up 0.07625. 0.07625 moles of that sulfuric acid, okay? Can I do this math problem without getting negative? Yes. So 0.098379 minus 0.07625 equals 0.022129. 0.22129. And what this is telling me is this is how many moles of the H2SO4 are going to be left over. That's H. Sorry, I'm writing with my mouse here. It's a little difficult. And these are my leftovers. So this reaction is going to use up all the sodium hydroxide. There'll be none left over. But at the end, there's going to be some moles of H2SO4 left over. Now, did this question ask us anything about water? No, it didn't. But let's fill it out so you can see how the whole table works. So how much water am I creating? Well, it's going to be based off my limiting reactant. So it's going to be 0.1525 moles of my sodium hydroxide times the ratio of the unknown water to the known unknown water to the, oops, well, that's not right. Good thing I double checked. What's the ratio of water to sodium hydroxide? It's 2 to 2. Okay, so what's 0.1525 times 2 over 2? Well, that's 0.1525 moles of H2O created. Okay. Now here's one they actually do want us to figure out. Let me move this over a little bit so I have more room on my screen. These aren't related to each other right here. I mean, if you wanted to draw more lines, you totally could. So I'm just going to kind of put like a little divider line here. See, like these are all separate, right? So this is all my sulfuric acid work. This is all my sodium hydroxide work. I always separate the products, the reactants from the products. This is all my water work. And here, this is all the sodium sulfate work. Okay. So how much sodium sulfate am I creating? I'm creating, based off the limiting reactant, okay, so 0.1525 moles of the sodium hydroxide times the ratio of the unknown sodium sulfate to the known sodium hydroxide. So that mole ratio comes from the balanced chemical equation. So I've got 0.1525 divided by 2, and that should be the same number right there. That's the same ratio, right? So how many moles of the sodium sulfate did I make? 0.07625. 0.07625. And that is going to be my moles of the sodium Na2SO4 produced. okay? I have done all the hard work now, okay? I figured out that sodium hydroxide is limiting. I have this many leftover moles of sulfuric acid. I've created this many moles of water, and I've created this many moles of sodium sulfate. However, a lot of the questions don't want moles, they want grams. Okay, so now we actually can start the second question. So what is the theoretical yield of sodium sulfate in grams? So hint, use the BCA table to find the moles of sodium sulfate and then convert to grams using the molar mass. Okay, so how many moles do we say? 0.07625. So 0.07625 moles of sodium sulfate, and that number came right here from my BCA table work. And now I want to get rid of moles and convert to grams. So I have to go to the periodic table and find the molar mass of sodium sulfate, which I happen to have right here. Sodium sulfate, there are 2 sodiums, there's 1 sulfur, and there are 4 oxygen. So our mass is 142.05 grams per mole. 142.05 grams per mole. So let's take out our handy dandy calculator of science, and we're just going to multiply by 142.05 grams. So how many grams do we have? This many moles times that many grams, 10.8313. Okay, now we're not going to use this number again, so now we can actually round it. In the original problem, we have 3 sig figs, so I actually want to round this to 3 sig figs. 1, 2, 3. Look to the right. Does the 3 round up the 8? Nope. So we're going to call this 10.8 grams of NaSO4. And that is our theoretical yield based on all the BCA table calculations. So if you put in 9.65 grams of sulfuric acid and 6.10 grams of sodium hydroxide, you will produce 10.8 grams of sodium sulfate. Okay, next one. This one, we've done all the hard work already as well. How much of the excess reactant will be left over? Well, we said that sodium hydroxide was limiting. The excess reactant is the H2SO4. Okay, so we have to convert the moles of H2SO4 left after the reaction, convert it from moles to grams. So 0.022129. Let me put that into my calculator. 0.022129. See, I don't want to round this number because I'll lose some precision if I round that before I'm finished. So 0.022129. That's my leftover moles of sulfuric acid, H2SO4. I'm going to put that over 1. And now I want to multiply by a conversion factor to convert my moles. So moles are going to cancel. See how it's in the numerator than the denominator? We want to go from moles to grams. So I've got to go to my periodic table. Oh, look at that. I have it written right up here, right? H2SO4. We know that it's 98.09 grams per mole. So how many grams are left over? So here's my number, moles times 98.09. And I'm going to get 2.1706. 2.1706 grams. Now, same thing. I'm given 3 sig figs. So now that I'm done with this number, I'm going to round it to 3 sig figs. 1, 2, 3. Look to the right. Does a 0 round to 7? Nope. So my final answer is 2.17 grams of that excess H2SO4, and that is left over after the reaction. Now let's just do kind of a common sense check. I started with 9.65 grams. Could there be 2.17 grams left over? Yeah, that makes a lot of sense. What if we got something crazy like 15 grams left over? Would that be possible? No. So this makes logical sense. It seems like everything's going fine. Okay, now for the very last step. This is all the theoretical work. These are all your calculations. But when you're actually in lab, things don't work out 100% perfectly. Some of the yield is lost. Maybe you didn't measure these things right. Maybe you didn't wait long enough for the reaction to complete. Maybe your lab partner spilled something. Maybe some of the salt got stuck to the container. There's all types of errors. So we have to actually analyze our percent yield. You usually don't get 100% yield. So if we theoretically calculated that we should have 10.8 grams of sodium sulfate, that's probably not what we're going to get. And they tell us they actually produced 10.5 grams. Now that's pretty close. That's not too bad. But we want to figure out what the percent yield was. So here's the equation. So the percent yield is going to be the actual amount recovered in grams. So this right here, this is the actual. This is what someone actually measured in lab. So they have 10.5 grams. And we're going to divide that by the theoretical amount from the BCA table, which is 10.8 grams. So you can see it's less, right? We actually got less out. So it's going to be less than 100% yield. You can have over 100% yields, and that means that your final product is contaminated, either with excess reactant or with water or some other mishap. And then we're going to multiply by 100. Okay, so we're going to take our 10.5 grams, divide by 10.8 grams, then times 100, and we get 97.2 repeating. So 97.22222%. Same rounding rules are going to apply. We want 3 sig figs. 1, 2, 3. Look to the right. Will that 2 round that 2 up? Nope. 97.2%, and that's our percent yield. That's it. We're done. We tackled probably the hardest stoichiometry problem you'll do, and this is probably the trickiest problem you'll do in chemistry this year. Thanks for working hard on this, guys. Make sure you show all your work. Bye.